Hey y'all, it's Ms. Blasky. Um, Today we're going to talk about how what we learned last unit in Unit 6 is going to apply towards acids and bases. So what we learned in Unit 6 was all about equilibrium. So equilibrium holds for weak acids and weak bases. Since strong acids and strong bases 100% dissociate in their solutions, they're not in equilibrium. They make no reverse reaction. There are no reactants being reformed from the products. But in weak acids and weak bases, we do have that forward and reverse reaction happening at the same time. So we are going to differentiate the equilibrium constant for acids and bases. K with a little a after it is the acid dissociation constant, or the acid equilibrium constant. And then likewise, Kb will be for bases. K, the magnitude of K works out the same way as it did for equilibrium. The larger the K value, so if K is large, that means that we have more products. The smaller K is, it means we have more reactants. So when we're talking about these weak acids and weak bases, they are going to tend to have smaller K values. The weaker the acid or weaker the base, the smaller the K value will be. The one thing that is nice about equilibrium in acids and bases compared to general equilibrium like we did in Unit 6 is that acid and base dissociation, or when they react with water to either gain or lose a proton, has a very set formulaic reaction. So you will see this often when we're talking about weak acids in general. They will write out HA instead of a specific acid. So A can be any anion with that H plus or proton connected onto it. So that HA acid reacts with water. Since HA is an acid, it is going to donate away a proton and make the conjugate base of A minus. The water is going to act as a base, accept that proton, and form the conjugate acid of H3O plus. Now, we also talked about that we could write out this reaction for acids without water. So we could just have HA in equilibrium with H plus and A minus. Either way of writing that reaction is acceptable. When we write an equilibrium expression from either of those reactions, we need to remember our rules about what is involved in equilibrium and what is not. So pure water, H2O, is a liquid. It is not going to show up in my equilibrium expression. So my equilibrium expression can either be the way it is typed on your page, based on this reaction. H3O plus is that hydronium ion, A minus is that conjugate base, HA is my acid. Or if we're using the same reaction without including the water in it, then our Ka expression would be H plus times A minus over HA. Remember that H plus and H3O plus, that proton H plus or the hydronium ion H3O plus, are interchangeable with each other. But in either case, the water does not show up in that equilibrium expression because pure solids and pure liquids don't show up in equilibrium. Knowing that information, we can either solve for a value for K, just like we did with equilibrium last unit, or if we know K, we can solve for the concentrations at equilibrium of any of the substances in that reaction. This is how we're going to get to the pH of weak acids. We cannot just take the negative log of the concentration of H plus like we did for strong acids. previously, because not all of that acid is dissociating. Not all of that acid is turning into and forming H plus ions. So we need to figure out how much dissociates first based on the K, find that H plus or H3O plus concentration from an ice chart, and then we can find the pH. So for example, if we want to calculate the pH of a 1 molar hydrofluoric acid solution, it is a weak acid. They give me the Ka value. I see that that Ka is small. Its exponent is 10 to the negative fourth. Just purely by the fact that they have given me a Ka that identifies this as a weak acid. Kas for strong acids don't exist. They are so large, they are infinite. So first thing we need to do is we need to write out the reaction for how that acid is going to be donating away its protons. Again, this case, it is written without the water. You could write it with the water, whichever way makes most sense to you. From that balanced equation, we can write an equilibrium expression, products over reactants, and we do know that K value, so we can substitute that into the equation. Once we have all of that set up, we can set up our ice chart. They said we have a 1 molar hydrofluoric acid solution. So that solution starts off initially on the I line with the concentration of the acid. Initially, at the very beginning, none of it has dissociated into H plus and F minus. Again, nice thing about this, these reactions for acids and bases are always only going to have a coefficient of 1. So we are not going to have exponents. We're not going to have 2x's or 3x's or anything. We just need to keep track of our pluses and minuses. Since the H plus and the F minus are zeros, they are going to have to be the plus X side. And my reactant, the HF, is going to have to be the minus X side. So once we do the math, we get an equilibrium concentration of HF as 1 minus X molar. And then the concentration of H plus and F minus are both X molar. We plug those values into our K expression. We get X squared over 1 minus X. In order to make our math a little bit easier, we can 5% rule away that X. And this format is going to be true for pretty much any weak acid equilibrium that you're going to figure out. So my concentration of HF, because we use the 5% rule, is just going to stay 1 molar. Multiply up both sides by 1, take the square root to find X. X is both the concentration of H plus and F minus. It is the same concentration. So we are used to doing equilibrium and stopping here. If the problem asks for your pH, this is where we need to do one extra step. We found the H plus concentration. We can use that H plus concentration now in our pH calculation. That pH equals the negative log of the H plus. So I take the negative log of that H plus value, which is 0.027 molar, and gives me a pH of 1.57 for this hydrofluoric acid solution. Just like we can use pH as a measurement of how much H plus is in the solution, how acidic or how basic something is, there is another value that we can use called the pKa. So anytime you see a P in front of something, P means the mathematical function of negative log. So the pKa is the negative log of the Ka value. pKa is used to talk about the strength of an acid. Just like from our Ka value, we can determine what extent that reaction is making products versus reactants. Larger Kas mean we have more products. Smaller Kas mean we have larger concentrations of reactants. The pKa, or the negative log of the Ka, is oftentimes used as just a shorthand version to determine the strength. So the pKa of a very strong acid is going to be very small, possibly even a negative number. That means our Ka of a strong acid is very large. So let's say it's 1 times 10 to the 20th. If I take the negative log of that, we're actually going to get out a very small or negative number. If I have a very small Ka value, meaning I have a very weak acid, when I take the negative log of that, I'm going to end up with a larger number. So larger pKa's are weaker acids. Basically, this number just gives us a quick glance kind of version to say how strong is this acid, or how likely is this acid going to dissociate lots of H pluses or only a little concentration of H pluses. We also can use this idea of Ka's to calculate the pH of polyprotic acids. Remember that we talked about polyprotic acids as being acids that can donate away more than one proton. So for example, I have the dissociations of phosphoric acid here on page 8. Phosphoric acid is a triprotic acid. It's H3PO4. If I look at just the first proton dissociation of H3PO4 donating away one proton and becoming H2PO4 minus, it has a Ka of 10 to the negative 3. Now then that H2PO4 is able to donate away another proton and become HPO4 minus 2. Notice how much smaller that Ka value is for that donation of the second proton than the first, and then donating away the third proton, going from HPO4 2 minus to PO4 3 minus, is even smaller. The official rules for Kas is that the Ka for the whole process of donating away all 3 of those protons would be Ka1 multiplied by Ka2 multiplied by Ka3. But for the most part, the dissociation that is going to provide the most impact on our pH is the one that is most likely to happen. In this case, the one that is most likely to happen is that first step, donating away that first proton. So if we ever have to do any calculations about polyprotic acids, we're really only going to focus on that very first proton donation. So if we needed to calculate the pH of a phosphoric acid solution, we would just use the Ka for step 1. So let's take a look at example 19. I'm going to have you work this problem out. So go ahead and pause your video, work through number 19, and I want you to calculate the pH of a 0.1 molar solution of hypochlorous acid or of bleach. So to calculate out the pH of the solution, they tell us that hypochlorous acid has a Ka value, which automatically tells us that it is acting as a weak acid. We should be able to write out the dissociation reaction for this hypochlorous acid. Dissociation reaction we mean by donating away the proton. So HOCl, we know it's in equilibrium because it is a weak acid, produces H plus, it donates away that proton, and the OCl minus is the ion that is left over. That is our A minus ion. Equilibrium expression based on that is H plus times OCl minus over HOCl. No exponents because everything has a coefficient of 1. Now we can set up our ice chart. Initially, they say we have a 0.100 molar solution of this. We have no H plus and no OCl minus initially, minus X plus X plus X, 0.1 minus X, X, and X for my equilibrium concentration. You might even be able to get to the point after doing enough of these problems where you might not even need to write out the ice chart to be able to calculate this. So X and X are my products. Reactant is 0.100 minus X. They specifically tell me that my Ka has a value of 3.5 times 10 to the negative 8th. 5% rule says I can remove that X and we can calculate this out. So 0.1 times 3.5 times 10 to the negative 8th, and then take the square root of that to find out what X is. My X value is my H plus concentration, which in this case comes out to be 5.92 times 10 to the negative 5th molar. To find the pH, I take the negative log of that H plus concentration, and I get a pH of 4.2. Every single question is going to be set up pretty much this exact same way. We also can do this exact same math for bases. If you go to page 9, we talk about weak bases. Weak bases are going to behave the exact same way. They have a Kb value, which measures how strong of a base they are. In order to write out the equilibrium expression, remember for bases, we always do have to include that water because that base needs a source of protons to be able to accept. So the base is going to react with water to make Hb plus, whatever that base is, with a proton on it, and then leave the hydroxide left over from the water that has donated its proton. But again, because that water is a pure liquid, it is not going to show up in the equilibrium expression. So we get BH plus times OH minus over B. Again, these Kb values should be small because these are weak bases. They are not going to produce much product. They're going to have much more concentration of reactant than they do product. Calculations work out the exact same way. Other interesting thing is that just like concentration of H plus and OH minus, the Kw comes into effect here, where Kw equals Ka times our Kb. So if we know the Ka of the acid, we can calculate the Kb of its conjugate base by using the Kw or the dissociation constant of water. That's all I got for you today. Make sure you work through some of these other example problems, and we will continue working on this in class. I will see you all later. Bye.